4.1 Antidifferentiation. Southwestern College, Professor Maria Olivas. Antidifferentiation. Objectives. Find an antiderivative of a function. Evaluate indefinite integrals using basic rules of antidifferentiation. Use initial conditions to determine an antiderivative. Section 1. Antiderivatives. Definition. A function uppercase f is an antiderivative of lowercase f if the derivative of uppercase f of x is equal to lowercase f of x for all x. Example 1. Show that uppercase f of x, which equals 1/3 times x raised to the third power plus 6x raised to the second power minus 4x plus 3 is an antiderivative function for lowercase f of x, which equals x raised to the second power plus 12x minus 4. So in order to show that capital or uppercase f of x is an antiderivative function of lowercase f of x, we need to find the derivative of uppercase f of x. I will now highlight in yellow part of the definition where it states uppercase f is an antiderivative of lowercase f. Then I will highlight in green the part that states the derivative of uppercase f of x equals lowercase f of x, which is a key part that we need to show. I will now draw an arrow pointing towards our uppercase f of x function. And next to that arrow, I will write down find the derivative, because this is basically what we need to do. We need to find the derivative of uppercase f of x. So let's go ahead and do that. The derivative of uppercase f of x is going to be equal to 3/1 times 1/3 times x raised to the 3 minus 1 power plus 2 times 6 times x to the raised to the 2 minus 1 power minus 1 times 4 times x raised to the 1 minus 1 power plus, and I'm just going to go ahead and write 0 for this because the derivative of any constant is 0. I am showing every little step for this derivative for the people that need it. The derivative of f of x is equal to, here the 3's will divide out and I'll just be left with 1's, and 1 times 1 is just 1, so we could just write x squared plus 12x minus 4. And this demonstrates that the derivative of uppercase f of x is equal to our lowercase f of x function. I'm going to highlight in yellow our lowercase f of x function. And I'm also going to highlight in yellow what the derivative of uppercase f of x was equal to. So you can see that they're equal to each other. I'm also going to write that it equals lowercase f of x. And I'm going to draw a cloud around our green highlighted part of the definition, pointing towards what we have just demonstrated, that uppercase f prime of x is equal to lowercase f of x. And that was the key part that we needed to show from the definition. And I'm going to put a little check mark at the end of that to show that I actually did show that. And I underlined the part show that because that's what I did. I showed that our capital f prime of x was equal to lowercase f of x. And I highlighted those in green like I did in the definition at the end to show that they were actually equal to each other. Example 2, name an antiderivative function for lowercase f of x equals 2x. I'm going to highlight the coefficient of 2, and I'm going to also write in our exponent of the x, which is a 1, and highlight that. We need to think of an expression that if I take the derivative of it, it will give me 2x. So how about x squared? Because if I take the derivative of x squared, if I put that 2 out in front, it'll give me a coefficient of 2. And if I subtract 1 from a 2, it'll give me an exponent of 1. So a possible function would be uppercase f of x equals x squared. That's one possible antiderivative function. Or another possible antiderivative function would be uppercase f of x equals x squared plus, let's say, like the number 5. Actually, we could use any number here instead of 5. I'm going to draw an arrow here going to the side, and I'm going to write uppercase f of x equals x squared plus c, where c can represent any constant. So we actually have an infinite number of antiderivative functions that we could use here, that if we take the derivative of them, they're going to give us that lowercase f of x equals 2x. When determining a general antiderivative function, you need to add a constant at the end. This is because taking the derivative of a constant is 0. And I'm going to go ahead and highlight all of that in yellow. I'm going to also draw a cloud around the part that says you need to add a constant at the end, because we don't want you to forget to do that. And I'm going to put a little star right next to that. Notation for the general antiderivative. This is called the indefinite integral. The integral of lowercase f of x dx equals capital F of x plus c. I'm going to draw an arrow pointed towards the elongated s in front of the lowercase f of x dx. This elongated s represents our integral sign. I'm going to draw a little line underneath the lowercase f of x with a little arrow pointing towards it. And this is going to be our integrand, or we can refer to this as our integrand function. Now I'm going to draw a little line beneath the dx with an arrow pointing towards that. And this is going to basically indicate which variable we are integrating with respect to. So I'm going to write here, this indicates that x is the variable of integration. And now I'm going to point a little arrow, or draw a little arrow pointing at the c that's on the right hand side of our equal sign. It's after the capital F of x, and it has a plus c. And that c is going to represent our constant. And we're going to refer to the c as our constant of integration. So this represents the notation for the general antiderivative. Basic integration rules. Number 1, integral of a constant. So the integral of k, where k represents a constant, dx equals kx plus c. I'm going to put a box around this integration rule. Let's go ahead and do an example for this. Let's call this example 1. The integral of 5 dx. Now remember what the dx stands for. The x represents the variable that we're integrating with respect to. So when we integrate this, remember we're going to be using an x. So this is going to be equal to 5x, and I'm going to highlight the x. here, plus c. And I'm going to put a box around that. Let's do another example. Let's go ahead and call this one example 2, the integral of negative 2 dt. This is going to be equal to negative 2t plus c. And let's put a box around that. So there you go. Let's do another example. Let's call this example 3, the integral of dy. So there's an imaginary 1 in front of that dy, so this is just going to be equal to y plus c, and we'll put a box around that. Number 2, the power rule. So the integral of x raised to the n power dx is going to be equal to x raised to the n plus 1 power all over n plus 1. And then we're going to put plus c out to the side here, so long as n is not equal to negative 1. Let's put a box around that. And then let's do example number 1, the integral of x raised to the 5th power dx. This is going to be equal to x raised to the 5 plus 1 power, all divided by 5 plus 1, and then we're going to put plus c out to the side. So this will simplify to x raised to the 6th power divided by 6, and then plus c. And we're going to put a box around that. I'm going to put a line here separating our next example. Example number 2 is going to be the integral of 1 over n raised to the 3rd power dn. So first off, we're going to write this equal to the integral of n raised to the negative 3 power dn. And now we can use that power rule. So that'll be n raised to the negative 3 power plus 1 all over negative 3 plus 1. And then we're going to put a plus c out to the side. And this is going to be equal to n raised to the negative 2 power over negative 2, and then plus c. And this can be simplified to negative 1 over 2n raised to the 2nd power plus c out to the side. And I'm going to just make this a little bit smaller so it will fit nicely. I'm going to put a big line here separating example 2 from our next example 3. And this will be example number 3. The integral of the square root, no, take that back, the integral of the cube root of t raised to the 2nd power, and then dt. This is going to be equal to the integral of t raised to the 2/3 power dt, which is equal to t raised to the 2/3 plus 1, but instead of 1, I'm going to write 3/3 all over 2/3 plus 3/3. And then remember there's a plus c out to the side. Now let's go ahead and simplify this. This is going to give me t raised to the 5/3 all over 5/3 plus c. And let's simplify this a little bit more. This is going to be equal to 3/5 t raised to the 5/3 power plus c. And if you wanted to rewrite this, we could also rewrite this as 3/5 times the cube root of t raised to the 5th power and then plus c. I'm just going to make this a little bit smaller so it will fit a little bit nicely in here. Perfect. There we go. And I forgot to box in my last answer, so I'm going to go back and I'm going to box in my last answer from example 2. And I'm also going to box in my answer for example number 3. Number 3, special case of the power rule. The integral of x raised to the -1 power dx is equal to the integral of 1 over x dx. So this, when we take the integral of this is always going to be equal to the natural log of the absolute value of x plus c. I'm going to put a box around that. I'm just going to move this up a little bit slightly higher, make it a little smaller, just so that I have more space for my examples. Example 1. The integral of 1 over p dp. This will be equal to the natural log of the absolute value of p plus c. And then we will box that. Let's go on to example number 2. The integral of m raised to the -1 power dm. This is going to be equal to the natural log of the absolute value of m plus c. And let's box that answer as well. All right, number 4, exponential functions. The integral of e raised to the x power dx equals e raised to the x plus c. And let's go ahead and put a box around that rule. Our next exponential rule is the integral of e raised to the kx power dx, which is equal to 1 over k times e raised to the kx power plus c. Let's go ahead and put a box around that rule. All right, so let's go ahead and do examples for our exponential function rules. Example 1, the integral of e raised to the t power dt. This equals e raised to the t plus c. Let's go ahead and box that in. And you know what? I think I'm going to change the boxes to all the answers of my examples to a slightly thinner box. So that way the boxes around the rules have a thicker box and they stand out more so you can see what the rules are in comparison to the examples that we've done. And that way I think it'll be easier to tell the difference between the two. Okay, let's go on to our next example. Example 2. That's going to be the integral of e raised to the -4x power dx. And this is going to be equal to, we're going to look at the coefficient in front of the x in our exponent part, which represents our k. So in this case, k is going to be equal to -4. So I'm just going to go ahead and just substitute every time I see a k there. I'm going to have -1 over 4 times e raised to the -4x power plus c. And we're going to go ahead and box that in. Number 5, constant multiple. So I'm going to have here the integral of k times f of x dx. So here k represents a constant multiple. So this is going to be equal to k times the integral of f of x dx. So when you have a constant multiple, you are allowed to factor that out of the integral. Let's go ahead and put a box around that. Example 1, the integral of 8x raised to the 9th power dx. And this, the constant multiple we have here is 8. So we can factor that out of the integral. So this is going to be equal to 8 times the integral of x raised to the 9th power dx. Now I can actually do the integration. So this is going to be 8 times x raised to the 10th power divided by 10 plus c. This equals 8/10 x raised to the 10th power plus c, which is equal to 4/5 x raised to the 10th power plus c. And we'll box that final answer in. Okay, so let's go ahead and move on to our next rule. Number 6, the sum and difference rule for integrals. So this rule basically says that the integral of the sum or difference of two functions is the sum or difference of the integral of the two functions. So the integral of open square brackets f of x plus or minus g of x close square brackets dx is equal to the integral of f of x dx plus or minus the integral of g of x dx. Let's put a box around that. All right, let's go ahead and do example 1 for this rule. The integral of open parenthesis 5x to the 4th plus 2x raised to the 3rd power minus 7 close parenthesis dx. So we're going to rewrite this as the integral of 5x to the 4th dx plus the integral of 2x raised to the 3rd power dx minus the integral of 7 dx. I'm going to use my constant multiple rule. I'm going to factor out my constant multiple, so I'll have 5 times the integral of x to the 4th dx plus 2 times the integral of x to the 3rd dx minus 7 times the integral dx. So I will end up here with, after I do my integration, 5 times x to the 5th divided by 5 plus c plus 2 times x raised to the 4th divided by 4 plus c minus 7 times x plus c. Now I'm going to highlight the 3 plus c's that I have here because in reality I don't need to write plus c 3 times. If you add a constant plus a constant plus a constant, it will give you a constant. So I'm going to put little red clouds around each one of those c's and draw arrows pointing over here to the right hand side of my screen, and I'm going to write c plus c plus c actually is going to just give us another c. It's just a constant plus a constant plus a constant is just equal to a constant. So it's not necessary for us to write 3 c's. It is sufficient with just writing one single plus c at the end. Okay, so if we simplify this, we will end up with x to the 5th plus x to the 4th divided by 2 minus 7x plus c. And we will go ahead and box that answer in. So that is going to represent our indefinite integral for this problem. Section 2, Differential Equations and Initial Value Problems. A differential equation is an equation that involves a derivative of an unknown function. Solving a differential equation means finding that unknown function. Example 1. dy dx equals 4x plus 3. Find y equals f of x. So if we're looking for this unknown function, this is what we're trying to find. I'm going to put a cloud around find y equals f of x. I'm going to write this as dy equals 4x plus 3 inside parentheses times dx. And basically I'm just writing this as the differential of the dependent variable is equal to the derivative times the differential of the independent variable. Now I'm just going to go ahead and integrate both sides of the equation. The integral of dy is y. And although there is a plus c, I'm going to put all my plus c's to the right-hand side of the equal sign, okay? The integral of 4x plus 3 dx is going to be 4x squared divided by 2 plus 3x plus c. Y equals 2x squared plus 3x plus c. This is my general solution. I'm going to put that in a box. I'm going to draw an arrow to it, and I'm going to write down the words general solution. An initial value or initial condition allows you to find the particular solution, not just the general solution. In other words, it allows you to find C. I'm going to put a cloud around the words "it allows you to find C" because that is the key part of finding a particular solution. Finding C and then substituting that value back in for C. All right, example 2. F prime of x is equal to 4 divided by the square root of x. If f of 1 is equal to 3, find y equals f of x. I'm going to go ahead and highlight the f prime of x. So it is important when you have this form of the derivative that you rewrite it. So we're going to rewrite f prime of x as dy over dx. So we're going to have dy over dx equals 4 over the square root of x. Now we're going to rewrite this as dy equals 4 over the square root of x times dx. Now we will integrate both sides of the equal sign. The integral of dy is y, and then this is going to be equal to the integral of 4 divided by the square root of x dx is going to be 4 times the integral of x raised to the negative 1/2 power dx. Now we will have y equals 4 times x raised to the 1/2 power divided by 1/2 plus c. We can simplify this a little bit more. Let's rewrite this as y equals 4 times 2 times the square root of x plus c. And we can simplify this a little bit further. We can multiply the 4 times the 2. So we'll get y equals 8 times the square root of x plus c. Okay, now we're ready to find our c value. Before I do that, let's go ahead and just make this a little bit smaller so I have more space to write on here on the screen. Let's write x equals 1. I know that x is equal to 1 based off of my initial value. So I'm highlighting the 1 in the f of 1 at the very top where it says f of 1 equals 3. And I'm drawing a little arrow pointing at that 1, and I wrote x equal to 1 right above it. Now I'm going to highlight the whole f of 1 equals 3, and I have an arrow pointing at the 3. And I have an arrow pointing at the 3, and I'm going to write y equals 3, because I know that that's my y value when x is equal to 1. So we're going to use this x equal to 1 value. We're going to substitute it in for our x into our equation. And then we're going to use that y equal to 3 value, and we'll substitute that in for y into our equation. And then we will solve for c. So let's go ahead and substitute those values. I'm going to draw an arrow here up to the top, and I'm going to rewrite my equation as 3 equals 8 times the square root of 1 plus c. So this is going to be 3 equals 8 plus c. I'm going to subtract 8 from both sides, and this will give me -5 is equal to c. Now that I have the value of c, I can go ahead and substitute that in, and that will find me my particular solution. So going back to my equation of y equals 8 times the square root of x plus c, I drew a cloud around it with an arrow pointing towards the right. I've highlighted my c value and my c variable over here, and I'm going to go ahead and substitute -5 there. So I get y equals 8 times the square root of x minus 5. I put a box around it. I have an arrow pointing up at my solution here, and I'm going to write right beneath it particular solution, because that's what this represents. This represents my particular solution. And I'm going to draw a little cloud around that, so you see that that's my final answer, because I do have a lot of other things kind of with clouds and highlighting. I want to make sure it stands out.